So in this slide I am explaining refraction at rarer medium. So let us start with again an interface xy, which is going to divide medium into two parts. Its upper part is a denser medium now, which is having a refractive index n1, and the lower portion is a denser medium which is having a refractive index n2. So now assume that a spherical wave is now moving towards the xy interface with a speed v1. Now we have to indicate the direction in which this spherical wave is moving, like this, by the arrow marks. It's one arrow mark is going to reach, or it is going to reach the point C on the xy interface. Now I have to take a part of this spherical wave. Part of spherical wave is a plane wave. We already studied it. So now that plane wave is now moving towards the xy interface, and that plane wave is not moving parallel to the xy interface. Because of this reason, or because of this angle, its one end touches the xy interface first, and its other end is away from the xy interface by a certain distance. So now this is called incident plane wave. So this incident plane wave has its one end, it's already touched the xy interface. I am marking that end as A, and its other end is B. So you have to draw one more vertical line. This vertical line is called normal to this xy interface, and this is the direction of incident plane wave, and the angle between the normal and the direction of the incident plane wave is called angle of incidence I. Now let us mark the direction in which the incident plane wave is moving. Now I have to assume that among the two ends A and B, B end is in rarer medium. It is now travel a distance BC to reach the xy interface, because its A is already reached the xy interface. B is away from this xy interface by a distance BC. Now we have to measure how much time this incident plane wave will take to travel from B to C with a speed v1. So let us assume that now it is traveling from B to C. So it has taken time t seconds to travel from B to C. It has taken t seconds. We have to assume that it has taken t seconds to travel from B to C. We have got a speed v1, because with this speed only it is traveling from B to C. It has the time duration is t seconds. Just multiply speed and time duration, you get the distance v1 into t. Now we are studying about this incident plane wave. Refraction of this incident plane wave at rarer medium. Means refraction take place in the rarer medium, not in denser medium. Initially the denser medium, the incident plane wave, initially it is traveling in the denser medium, and afterwards it is enter into the rarer medium. Refraction take place in the rarer medium. So that is why this heading is like this: refraction at rarer medium. Means refraction take place in the rarer medium. Now its A end is already touched the interface xy. Now it is going to travel certain distance in the rarer medium. In the denser medium, its speed is less, whereas the incident plane wave will enter into the rarer medium. It moves faster. Uh, because of this reason, it is going to cover larger distance compared to the distance BC traveled in the denser medium in a same time t seconds. It is going to cover larger distance in the rarer medium, because it is speed is more in the rarer medium. The speed of incident plane wave is increases once it enters into the rarer medium. Let us assume that now it is entering into the rarer medium. It has covered larger distance. You can observe here. You can observe the both distance BC and the distance covered in the rarer medium. If you compare both, this distance is more than the distance BC traveled in the denser medium. We can easily calculate, because time duration is t seconds. We have to assume that once it enters into the rarer medium, its speed will v2. In the denser medium, its speed is v1. We have to assume that in the rarer medium, the speed of the incident plane wave is v2. So by multiplying this speed and time, then you get a distance covered in the rarer medium. Before that, I am marking the angle of refraction. This is the direction of refracted plane wave, and this is the normal. The angle between the normal and the direction of refracted plane wave will be called as angle of refraction, and the distance covered easily calculated by multiplying the speed in the rarer medium and the time duration. If you draw the before drawing the this line, I would like to explain how to construct the refracted plane wave in the rarer medium. To construct the refracted plane wave in the rarer medium, we have to take this distance v2 into t as a radius. The distance covered in the rarer medium, which is v2 into t, we have to treat this distance as a radius and a as a center. Then you have to construct one sphere around the point A. This is a sphere, a big sphere around the point A, which is having a radius v2 into t. Now from the point C, draw the tangent so that it touch the sphere at point E. Now this CE will be called as refracted plane wave, and this is the direction of refracted plane wave. This is the direction of incident plane wave. Both are different here. So now with this complete diagram, we are going to derive, or we are going to explain critical angle and the total internal reflection using Huygens principle. Let us move to next slide here. Now with this diagram, there is no need to take or draw this complete sphere around the point A. If you take a part of sphere in the denser medium, if you show the part of sphere in the denser medium, it will be more than sufficient. So you have to draw this diagram with a proper labeling: incident plane wave, refracted plane wave, angle of incidence, angle of refraction. So you have to indicate all this. Then for the triangle, you have to take two triangles, so A, B, C, and another triangle is ACE. For the triangle ABC, angle BAC also equals to angle of incidence, and angle ACE is also equals to angle of refraction. This is according to the principles of geometry. Then with this marking, with this proper labeling, let us move to the derivation part. So from the figure, we have to take the sine of this I value. For the triangle ABC, for the triangle ABC and for the angle I, BC is the opposite side and AC is the hypotenuse side. We have written here sin I equal to BC upon AC. The value of BC is V1 into T divided by AC. You have to write it as equation number 1. So next we have to take the sine of R value. For the angle R, AE is the opposite side and AC is the hypotenuse side. AE upon AC, the value of AE is V2 into T, V2 T divided by AC. Write it as equation number 2. Then take the ratio sin I by sin R equal to V1T divided by V2T, because AC will get cancelled, even T also get cancelled, leaving only V1 upon V2. You have to express this, or you have to rewrite the value of V1 and V2 in terms of the absolute refractive index N1 and N2. V1 equal to C by N1, V2 is equal to C by N2, where N1 and N2 are the absolute refractive index of this denser medium and rarer medium. And here C get cancelled, leaving only N2 upon N1. That means sin I upon sin R equal to N2 upon N1, or we can rewrite this equation as N1 sin I equal to N2 sin R. This is Snell's equation. Now we have to redefine this angle of incidence I. As we increase the angle of incidence, gradually the angle of refraction also increases. But for a particular value of angle of incidence, the angle of refraction becomes 90 degree. That means the refracted plane wave will graze the surface. Means the angle of refraction becomes equals to 90 degree. So before that, I'm again rewriting one more step. N21. N21 means N2 is here only. I'm bringing this N1 to the right side. It becomes N2 upon N1. N2 upon N1 or N21, both are same. N21 means N2 upon N1 or refractive index of second medium with respect to first medium. If you write N21, then it will be sin R by sin R. Then for the redefining purpose, I am taking the value of this angle of incidence for a particular value. For a particular value of angle of incidence, the angle of refraction becomes 90 degree, which means I am redefining the angle of incidence. When the angle of refraction becomes 90 degree, then the value of angle of incidence at that point will be IC. This is called critical angle. Suppose if you increase the angle of incidence beyond the critical value, then there will be no refraction in the rarer medium. So incident plane wave hits the XY surface and reflected back into the same medium. So this concept is called total internal reflection. So for that purpose, I am redefining. Redefining the angle means we have to write the value of this angle of incidence for a particular value of angle of refraction. For angle of refraction, when it becomes 90 degree, then the value of angle of incidence will be called as the critical value of angle of incidence. It is called as IC. As you know, sin 90 degree, sin 90 equal to 1. So N21 equal to sin IC upon sin R, or if you take the reciprocal of this equation, instead of N21, if you take 1 upon N21, then 1 upon N21 will be N upon N12. 1 upon N21 is nothing but N12. N12 means it is N1 upon N2. N21 means N2 upon N1. N21 means refractive index of second medium with respect to first medium. N12 means refractive index of first medium with respect to second medium. So you have to ask one, you might have a question in your mind, why I am writing N12 instead of N21? Because I have already redefined the angle of incidence for which the total internal reflection take place. If the angle of incidence greater than the critical value, then total internal reflection take place, isn't it? Then for which particular value of angle of incidence the reflection, total internal reflection will take place, that I have to write. Means I have to write the refractive index of the denser medium in which the total internal reflection take place. Total internal reflection is taking place in the denser medium, not in the rarer medium. So that is why I am taking the refractive index of first medium with respect to second medium instead of refractive index of second medium with respect to first medium. So if I write N21, it will be refractive index of second medium with respect to first medium. But I have, for the redefining the angle of incidence I as a IC, total internal reflection is taking place, and total internal reflection is taking place not in the rarer medium, it is taking in the denser medium. That is why I am writing N12, refractive index of first medium, that is refractive index of denser medium in which the total internal reflection is taking place. N12 is equal to sin R by sin IC. Sin R means sin 90 degree. Sin 90 equal to 1. So 1 upon sin IC. This is a very, very important equation you should remember. So the conclusion part is, once the angle of incidence reaches the critical value, if you increase the angle of incidence beyond the critical value, then there will be no refraction. There will be only total internal reflection. This is how we have to explain the refraction at rarer medium. For the refraction at rarer medium, you have to draw the diagram, complete diagram with a proper labeling, and then you have to write the value of sin I and sin R, and you have to mark it as equation 1 and 2. Then you have to take the ratio sin I by sin R. You can directly write sin I upon sin R as V1 by V2, but you have to write the value of v1 and v2 as c by n1 and c by n2, then the equation turns into sin I by sin R equal to n2 upon n1. Afterwards, if you rewrite this equation, then you get a Snell's law, that is n21 equal to sin I by sin R. Then if you redefine the angle of incidence I as a critical value of angle of incidence, then the sin R becomes equals to 1 because R becomes 90 degree. So in such case, you have to write the refractive index of first medium with respect to second medium as 1 upon sin IC. So here you have to conclude that once you increase the angle of incidence beyond the critical value, then there will be no refraction. There will be only total internal reflection. This is how you have to explain the total internal reflection using Huygens principle.